Welcome to the Deep Dive. Today we're plunging headfirst into quantum computing. It's a topic that, honestly, sounds like pure science fiction, right?
It really does.
But it's moving so fast from labs towards, well, reality. It promises to tackle problems we thought were basically unsolvable.
Things like developing new medicines, maybe, or completely changing cybersecurity as we know it.
Exactly. So we've pulled together some really insightful material for you. We looked at Aja Al-Hamadi's book, Quantum Revolution, and also a great article by Kabilan M., The Future is Quantum.
Yeah, both really good reads.
Our goal today, our mission for this deep dive, is to really unpack what quantum computing actually is. How is it so different from the computer or phone you're listening on right now? And explore what it could do, the amazing potential, but also, let's be real, the big hurdles that are still in the way.
And these sources, looking at them together, they give you a really full picture. You get the basic physics right through to the actual real-world implications. So we'll start with those basics, the building blocks. Then kind of get into the why does this matter part.
Right.
And then wrap up with the challenges and, what's next? What does the future look like?
Perfect. Okay, let's start there. We all kind of get how normal computers work, right? It's bits, zeros and ones.
Binary, yeah, on or off.
Processed through logic gates.
Yeah.
Simple enough, conceptually at least. But then you throw quantum in there. How does that just flip everything on its head? What makes it so different?
That really is the fundamental question, isn't it? Classical computers are like those light switches you mentioned, definitely on or definitely off, 0 or 1. Quantum computers use something different, qubits. Now, because of a quantum effect called superposition, a qubit isn't just stuck at 0 or 1. It can actually exist in a combination of both states at the very same time.
Hey, hold on, both at once.
Yeah. Think of like spinning a coin while it's in the air before it lands. It's kind of both heads and tails simultaneously, right?
Okay, I can sort of picture that.
It's a bit like that. Until you measure it, the qubit is in this fuzzy state of possibilities. But here's where it gets even weirder, and honestly more powerful. Entanglement.
Right, I've heard that term. Sounds complicated.
It is mind-bending. Imagine you have two of those spinning coins, maybe miles apart, but they're entangled. If one finally lands on heads, you instantly know, without even looking, the other one must be tails. Their fates are linked.
Instantly. Across distance.
Instantly. Doesn't matter how far apart, that's entanglement. It means the state of one qubit is directly tied to another. And that connection lets quantum computers explore a massive number of possibilities all at once, tackling calculations that would take a classical computer, well, longer than the age of the universe.
Wow. Okay, superposition and entanglement.
Yeah.
So qubits aren't just bits, they're bits plus possibilities linked together. That's wild. But how do you control these things if they're so fuzzy? How do you make them do useful work? What are the quantum logic gates like?
That's the next piece of the puzzle. If qubits are the fundamental units, then quantum gates are the operations you perform on them. They're like the instructions. But instead of working on definite zeros and ones like classical gates...
They work on those probabilities, those combinations.
Exactly. They manipulate the probabilities of the qubit being 0 or 1, or rotate its state in this abstract space. And when you string these quantum gates together in a specific order, you create a quantum circuit. That's essentially your quantum program.
Okay, so a circuit tells the qubits how to interact and evolve.
Right, to perform a calculation. And the real magic comes from the algorithms designed specifically for these quantum circuits. They leverage superposition and entanglement in ways classical algorithms just can't. We're talking things like Shor's algorithm.
Yes, the one that scares cryptographers.
That's the one. It can factor large numbers incredibly quickly, the very thing that makes most current online encryption secure.
So it could, theoretically, break modern encryption.
In principle, yes. A large enough stable quantum computer running Shor's could. That's a huge motivator for quantum research. Then you've got Grover's algorithm. It's amazing for searching through unsorted data.
How so?
Imagine searching a massive database. Classically, you might have to check, on average, half the entries. Grover's algorithm gives a quadratic speedup. It can find the item much, much faster by checking many possibilities at once using superposition.
So turning millions of checks into maybe thousands.
Something like that, yeah. It's a significant speedup. And this ability to solve certain problems exponentially faster or just make currently impossible problems solvable, that's what we mean by quantum advantage.
Quantum advantage. Okay, that brings us to the so what factor. What does all this mean for us, for different industries, for the world? The potential applications sound pretty revolutionary.
Oh, they absolutely are. The impact could be enormous across so many fields. Let's start with cybersecurity, since we mentioned shores. Because traditional encryption is vulnerable, there's this huge push now for quantum-resistant cryptography, new algorithms that even a quantum computer couldn't easily break.
So building defenses before the threat is fully realized.
Precisely. And also exploring things like quantum key distribution or QKD, which uses quantum physics itself to guarantee secure communication. It's not just based on mathematical difficulty, but on fundamental laws.
Interesting. Okay, beyond security.
Think about drug discovery and pharmaceuticals. Designing new drugs involves understanding incredibly complex molecular interactions.
Simulating how molecules behave.
Exactly. Classical computers struggle with the complexity at that scale, but quantum computers are naturally suited to simulate quantum systems like molecules. This could massively speed up discovering new drugs, understanding diseases, maybe even paving the way for truly personalized medicine based on your specific genetic makeup.
Wow, that alone will be transformative.
Totally. And it extends to materials science, too. Designing new materials with specific properties, maybe superconductors that work at room temperature, or super efficient solar cells, or lighter, stronger materials for aerospace. Quantum simulation can help us design these from the atom up.
And what about optimization? You hear that word a lot.
Yeah, so many industries face these incredibly complex optimization problems. Think logistics. Finding the absolute best routes for a global shipping network, considering fuel costs, delivery times, warehouse capacity, demand.
Millions variables.
Exactly. Quantum computers, by exploring many possibilities simultaneously, could find optimal solutions much faster than classical methods. This applies to finance, manufacturing, energy grids, almost anywhere you have complex systems to optimize.
It really does sound like it could touch almost everything.
Yeah.
But it also sounds incredibly difficult to build and control these machines. You mentioned qubits are delicate.
That's the flip side, absolutely. The challenges are immense. You hit on a key one, decoherence.
Decoherence, what exactly is that?
It's basically the enemy of quantum computation. Qubits need to maintain their delicate quantum states that superposition and entanglement to work. But they are incredibly sensitive to any interaction with their environment. The slightest vibration, a tiny change in temperature, stray electromagnetic fields
And mess them up.
can cause them to lose their quantum properties, to decohere back into boring old classical bits. Maintaining that quantum state long enough to do a complex calculation is a massive engineering challenge.
So you need extreme isolation, super low temperatures.
Often, yes, different types of qubits have different requirements, but generally they need very controlled environments. And then you need sophisticated quantum error correction. Just like classical bits can flip accidentally, qubits can suffer errors, and correcting those errors without destroying the quantum state is another huge area of research.
Okay, decoherence and errors. What else?
The other big one is scalability. Current quantum computers, the ones making headlines, might have tens, maybe hundreds of qubits, sometimes a few thousand, but stability is key.
It sounds like a lot, but
But for the truly world-changing problems, like breaking complex encryption or designing complex molecules, scientists estimate we'll need machines with thousands, maybe even millions of high-quality, stable, interconnected qubits.
millions. Wow. That's a huge leap from where we are now.
It's a monumental leap. It requires breakthroughs in physics, engineering, material science, computer science, the whole stack, both the hardware itself and finding even smarter quantum algorithms that perhaps don't need quite so many qubits.
It sounds like a global race is on then. Who are the main players pushing this forward?
Absolutely, it's a global effort. You have the big tech giants, IBM, Google, Microsoft, Intel investing very heavily. They see the long-term potential. But you also have a really vibrant ecosystem of startups, companies like IonQ, Rigetti, Sequantum. They're often exploring different approaches to building qubits, pushing innovation.
And governments, too, you mentioned.
Definitely. Governments worldwide see quantum computing as strategically vital, pouring billions into research programs, fostering collaboration between academia and industry. In terms of impact, while it'll eventually touch everything, people often expect the first big returns might be in finance for optimization and risk analysis and maybe pharmaceuticals or materials science due to that simulation capability.
Okay, so progress is happening, the investment is there, but the challenges are very real. For listeners, for businesses thinking 5, 10 years ahead, what should they be doing now? How do you prepare for something that feels both inevitable and maybe still a bit far off?
That's the key question, isn't it? And the sources give some pretty clear advice. First and foremost, Stay informed. You don't need to become a quantum physicist overnight, but understanding the basics, tracking the progress, and thinking about how it might impact your specific industry or job function is crucial.
Just keeping an ear to the ground.
Exactly. Second, maybe explain quantum research more actively. If you're in a larger company, perhaps look into partnerships with universities or some of those quantum computing firms. Start playing with the quantum software development kits that are available now. Get a feel for it.
Dip a toe in the water.
Right. And third, circling back to security, invest in cybersecurity readiness. Understand the threat quantum computing poses to current encryption and start learning about, and maybe even planning for, the transition to quantum-safe cryptographic methods. That's becoming increasingly urgent.
Don't wait until Shor's algorithm is running on a big machine.
Please don't. And finally, maybe the most important thing long-term. Think about talent and upskilling. There's already a growing demand for people who understand quantum computing, not just the physicists, but software engineers, algorithm developers, people who can bridge the gap between quantum potential and business problems.
So training your existing team or hiring people with these new skills.
Both. Building that quantum literacy within your organization will be critical to actually harnessing this technology when it reaches maturity. You need people who can identify the opportunities and know how to apply the tools.
Wow. Okay, what an incredible journey through the quantum realm. We've gone from, the absolute basics of qubits replacing bits.
A fundamental shift, yeah.
To these mind-bending algorithms like Shor's and Grover's that promise to solve problems we literally couldn't solve before.
Problems that were just intractable.
But also facing down those really tough challenges, decoherence, errors, getting to millions of qubits. It really feels like we're on the edge of something huge.
The progress, when you look at the big picture, it's undeniable. It's genuinely exciting. The potential to really reshape things is there.
And the sources we looked at, they really drive home that point.
Right.
Okay, maybe mainstream quantum computing is still a few years out, maybe more for some applications.
It's not tomorrow, for sure.
But the pace of innovation is just breathtaking. It really makes you stop and think. If we gain this power, this ability to process information at the quantum level, what other problems that we currently label unsolvable might finally crack open?
That's the big question. Curing diseases we can't touch now. Understanding consciousness. Designing perfect energy solutions.
Exactly. It feels like the possibilities are immense. It really does seem like a future that will belong to those who start preparing for it, thinking about it today.